In this video, we're still looking at our Shunt-Series configuration for our current amplifier. Now that we have our transfer function, let's look at our input resistance. And so our input resistance, I'm going to define as looking into our amplifier here. So looking into this point is where I'm defining my RIF. And so before we start doing our analysis, we can kind of see big picture. If I can relate my input current I sub I to that input voltage V sub I, then I can find my RIF. So let's start doing that by writing a KCL equation we had from our previous video, which relates our input current to our feedback and our error current. So we can say our input current is equal to our error current, I epsilon, plus our feedback current, I sub FB. And like we saw last time, we know that our feedback current is actually equal to beta I times I out. Well, we know that our I out is actually just equal to AI times I epsilon. And so the reason for that is because, remember, we've short-circuited this output so that our R naught is not having any effect. So now I have I epsilon plus, and I have my beta I still hanging out here. And now we're substituting our I naught for A sub I times I epsilon. So what we can do then is we can solve this for I epsilon, and we can say I epsilon is equal to our input current divided by the quantity of 1 plus beta I times A sub I. So we get something that looks like that. Okay, so now that we know this I epsilon, we can use that I epsilon to figure out the value for this V sub I, our input voltage. And so we can do that by saying our input voltage is just I epsilon times this Ri right here. So let's say our Vi is equal to I epsilon times Ri. So that's just going to be equal to Ri divided by that quantity 1 plus beta I times A sub I. Okay, so now we are at a point where we can do what we said at the start of the video. So we're going to say R sub IF is equal to that input voltage divided by our input current. And so if we're just taking this equation up here and we're dividing through by I sub I, of course, all that's going to do is get rid of that I sub I in the numerator. And we have R sub I divided by the quantity 1 plus beta I times A sub I. So what we can see is, in this case, our input resistance is being decreased. So we have a decreased input resistance. And so, like we saw with our voltage source, this is actually going to be desirable for our current source. And so we can look at a simple current divider circuit for current input. Okay, so what we can do to sort of reinforce that is if we think we have some current here, which is our input current, and the simplest current divider circuit, we have our sort of series resistance with that current source RS, and then we can approximate that amplifier with feedback network as having this input resistance R sub IF. And so ultimately, this is going to be the current that goes in to get amplified. So let's call this I amp. And so we want this I amp to be as close to I input as possible, because of course we want to be amplifying the signal that's being input. We don't want to lose much of that signal as we're sending it to the input. So what we know is if we have sort of two resistors here, we can say that our I amp is equal to our input current, I sub I, times, now in the denominator we have the sum of these two resistances, Rs plus RIF, and in the denominator, if we're interested in the current in resistor R sub IF, we're actually going to put the opposite resistor in the numerator, Rs. And so remember, if we look at what's happening to our input resistance, we know it's getting small. So this beta I times AI is going to be a relatively large value. So what we can say is this RIF is very small. So RIF small. And so if we wanted to make sort of a rough approximation, we can say, well, maybe it's going to be much less than RS, which means that this would be approximately equal to our input current II as we wanted in the first place.